Hi, this presentation will talk about how to compute normals for parametrically defined surfaces. This will include surfaces of rotation, for instance, in our project number 4. Parametric surface is given by a vector valued function. Parametric surface, or parametrically defined surface, is given by a function f of uv, which is defined with two parameters, u and v, and gives you a point f1 of uv, f2 of uv, f3 of uv, where the f1, 2, and 3 functions are giving you the z-coordinates of the point f uv. So you'll notice f is vector valued. I've got a vector sign over here. That means it's a vector valued function. Or think of it as giving you points in R3. Whereas the functions f1, f2, and f3 are scalar valued. They're giving you scalar values, which are the values of the x, y, and z coordinates of a point in R3. So just as a simple example here from Project 4 in fall 2020, we have a surface of rotation which can be defined as f of r theta, just renaming u and v to r and theta, to be, we rotate angle theta around the axis j, the point r sine of r over r 0. So the graph here of this function sine of r over r, if we have the x-axis here and the y-axis here, think of x as equal to r, and the function looks something like this, a decreasing sine function, which is then rotated in 3 space around the y-axis to generate a surface of rotation. So we've got a parametrically defined surface. The two parameters in this example are r and theta. As they vary, f of r theta takes on points in R3, and those points form the surface. So more generally, we have the following picture. We've got f of uv is defining some surface, which I can think of as sort of roughly patch-like. So I think of as u ranges from some minimum value to some maximum value. It might be u min to u max. U values, and v ranges from some minimum value to some maximum value. Okay, so this is the v values, and as they range, the values of u and v range, we generate some surface in R3. And you can think of these lines I've driven as being drawn. Lines I've drawn as being the places where u is constant going up and down and v is constant going sideways. As u and v vary, we get points on the surface here. And so remember that f of uv, it's f1, f2, f3, where f1, f2, and f3 are all functions of u and v. So we want to look at the partial derivatives here. So we look at the partial derivative of f with respect to u, which we can write in shorthand notation f sub u. This is just the same as the partial of f1 with respect to u, partial of f2 with respect to u, partial of f3 with respect to u. So again, the partials are scalar valued, of course, and their partial of f1 with respect to u is a function of u and v. So we can graphically draw these partials based on the idea that the partial derivative is the rate of change. So if we think about a point, suppose I've got a point here on the graph, and we're looking at this is f of uv for some value of u and v. The partial derivative with respect to u is going to give you the rate of change of f with respect to changes in u holding v fixed. So a v fixed line is going across, so the partial with respect the fu vector is going to be tangent to this line I drew with constant v values, because v is fixed I have a typo here I'd better fix. This is a u, and u is varying, and we're traveling along that curve, so the rate of change is tangent to the curve at that point. Whereas the partial with respect to v is similar. That's f sub v, partial f, partial u, is partial f1 with respect to v, partial f2 with respect to v, partial f3 with respect to v. And graphically up here, it's going to be tangent along the other direction. And the point here is these two partial derivatives are tangent to the surface, and in the general case, they're not going to be collinear. So if we take n to be f sub u cross f sub v, this will be normal to the surface, provided this cross product is non-zero. We can certainly have cases where it does turn out to be zero, and then we need to use other methods to figure out the normal vector at that point. But in most cases, most places on most surfaces, at least well-formed surfaces with nice formulas, we'll get a non-zero cross product. If we want a unit vector, we could use fu cross fv divided by the norm, the magnitude of fu cross fv. Then this will be a unit normal to the surface. So that's our formula. I'll circle this one here. This gives us a very simple formula for computing the normal using the parametric formula. Let's do a couple examples. The first one will be an upside-down parabola. So let's try the function y equals 1 minus x squared minus z squared, which actually doesn't really look like a parametrically defined function at all. We want the graph of that thing, but we can make it into one by, we're going to use f of uv equals u, 1 minus u squared minus v squared, v. So basically what we're doing here is we're thinking of u equals v, u equals x. Basically what we're doing here is we're thinking of u equals x, v equals z, and then of course y is 1 minus u squared minus v squared. The picture of this thing looks like a upside down parabola starting at the center of y equals 1. It looks something like this. Okay. And this general method can be used to take any function of two variables, y equals some f of x, z, and make it into a parametric surface. So in this case now, we then look at the partial of f with respect to u, and that's equal to 1 minus 2, 0. And the partial of f with respect to v is equal to 0 minus 2v, 1. If we take their cross product, partial f cross partial u cross partial f partial v, we just use the usual cross product formulas. So it's minus 2u times 1 minus 0 times something, so that's minus 2u. That's, for here, it's 0 times 0 minus 1 times 1, so it's minus 1. And here we get minus 2v for the third component. And this is supposed to be normal. Now this is, you notice the middle component of y is negative. It's pointing downward, so this is a normal, not a unit normal, pointing downward. In many applications, we're typically wanting to have a particular notion for the normals, whether they're pointing upward or downward. For an upward pointing normal, you could just negate. And if you just negate, then we get 2u, 1, 2v. And of course, u equals x and v equals y, v equals z, so we could use 2x, 1, 2z would be the same thing. For another example, let's try a surface of rotation. And here I'm going to actually not really do it with the cross product method at all. I'm just going to use the rotational symmetry. It really is the same thing, but I'm just not going to use the formula. I'm just going to try to eyeball what's going on. So rotational symmetry, here I've got a rotational symmetry, so we're rotating the graph of h of r greater than or equal to 0, by around the y-axis. So what I really want to do is I want to take the points x, h of x, 0. So I'm thinking of replacing r by x and setting z equal to 0. And then I want to rotate that around the y-axis. So that's r theta j of this. So the graph of this thing, here I've got some function h of x is the height. So this is the x-axis. This is the y-axis. This is the curve where y equals h of x and z equals 0. And then I'm going to rotate this thing around the y-axis to make a surface of rotation. So the idea here is to first figure out a normal just to this curve lying over the x-axis. See, if the curve is lying over the x-axis, we've just got a normal curve in 2 space in the xy plane, and we know how to find the slope of this. So the slope of this thing, so the slope is h prime of x is the slope of that line there. This other normal vector has slope -1 over h prime of x. Okay, and we have to watch out, h prime of x is 0 might cause troubles, but that will disappear when we do this transformation. So we can do a vector with slope -1 over h prime of x, for instance, in the xy, this is in R2 now, in R2. A vector with slope h prime of x is, for instance, there's quite a few of them, but you could use negative h prime of x 1, because the change in y over change in x is the right ratio. So we can switch to yet another color. There's some vector here, which is negative h prime of x 1. And we can then think about rotating this vector around the y-axis. Let me put a 0 for the x-coordinates. It's moving back to R3. We make z equal to 0. And then we can just think about the normal vectors can be just obtained, since the surface is obtained by rotating this curve around the y-axis. The normal vectors can be obtained by rotating the normal vectors around the y-axis. So n of r theta will just be r theta j of negative h prime of x 1, 0. which can be written out very easily in terms of sines and cosines and negative h prime of x. So that's this example here. This kind of computation might be the easiest way to do the programming project, but it does depend on being able to visualize slopes a little more carefully as compared to just plugging into the parametric equation. You could certainly also plug this formula, rewrite this in terms of sines and cosines, take the partial derivatives, take the cross product, and also get the same formula for the normal vectors. Final comment is these normal vectors are not necessarily unit vectors. If you need them to be unit vectors, you should divide by their magnitude. But this will work even for h prime of x equal to 0. In that case, the slope is 0 and the vector will be pointing straight up. And that's it for this presentation.